Okay, let's go ahead and get started, folks. I think most people have made their way over from the lightning talk session. Welcome, everybody, to the last session of the day. I am so excited to introduce Dr. Brooke Anderson, who is going to be leading this workshop. She is an associate professor of epidemiology at Colorado State University, and her research focuses on the health effects of climate-related disasters and includes the development of open source software for environmental epidemiology. And today she's going to be talking to us about some of the really cool resources that she's developed and made publicly available for assessing hurricane exposures for the purposes of epidemiological research. So thank you so much, Brooke. I am going to let you go ahead and take it away and share your screen. For the audience, you will be able to unmute yourself and ask questions if you have them. If you have pressing questions while Brooke is talking, she has said that you are welcome to unmute yourself and ask them. She won't be able to see the Q&A as she's talking, but hopefully we'll have time for more detailed questions at the end. Take it away, Brooke.
Thank you so much, Rachel. I'm really excited to be here. I wasn't able to watch the very first things this morning, but I did watch some of the lightning talks. And yeah, I was really excited to join in on that. So let me get things shared. And can someone confirm that you can see the slides?
Yep, looks great.
And they're changing? Okay.
Yes.
Perfect. All right. So what I want to talk about today, I'm going to start with giving an overview of what we'll do in this workshop. And it's not going to be so much a workshop in terms of having you stop and do a lot of things, but I will give you some examples that you can take home and use later. And I've put the slides in the chat, and I think if they need to repeat doing that so everybody can get them, you are welcome to have these slides. So some of the code examples I'll go through a little bit more quickly, but they are with the intent that if you wanted to try them out later, you could do that. So what we'll do this afternoon, there are many hazards that are associated with tropical cyclones, and in 30-45 minutes, it would not be enough time to cover exposure assessment for all of those. So one we'll focus on here are high winds, and I want to get a little bit more deeply into talking about those. We'll discuss how wind intensity can be measured for tropical cyclones, and then we're going to talk about how to leverage that for exposure assessment for epidemiology studies. And I have to say, from seeing some of the talks before, it looks like people are doing a lot of the things that I'm going to be talking about here in some of the studies, which again was exciting to see. So for some of you, you might already be doing some of this, and it might be more of an opportunity to hear some of the background and have some more insights in how to answer reviewers when they ask you questions about how you're doing this, and to share with your colleagues. So I'm going to focus on the principles of it because I want this to be widely applicable. But I'm also going to show examples from a set of R packages that my research group has developed and made available over the years. All right, so we're going to start by talking about central measures of storm intensities, and we'll focus some on storm track data. Then we'll move into a discussion of wind field models. And we'll talk about how that has an advantage over these central measurements in terms of being able to estimate winds that are local to study subjects. We'll talk some about how those can be used for exposure assessment, because of course that's something that has come out of atmospheric science, but it's a tool we can use in epidemiology. We'll also talk a bit about this idea of using that for binary exposure classification versus continuous measures of exposure. And then if we have time at the end, I want to briefly discuss some alternatives to wind field modeling. And those will include both other ways that you can measure wind, but also thinking about other hazards of tropical cyclones. For a lot of these concepts, they're covered in an article that I would love to share with all of you. So I think they're going to put that in the chat so everybody can have a copy and read through. We don't have a lot of time today, and there are a lot more details and a lot more things you can follow up on in this article. So I hope you will find that useful. All right, the last note before we get into the content, we're at the end of a few hours of talks, and I know attention can start to wane a little bit. So as I developed this, I focused on sharing the information in a way that's a little bit more top level, that's very visual, and hopefully is very engaging for this last session today. For full citations and to really get deeper dives into some of these concepts, you'll have the slides and you can follow up with those. The packages I'll talk about have vignettes that have more detailed examples you can go into. And then also the paper that I just mentioned is an excellent source to go into a really deep level when you have time and have just had your coffee and are ready to digest more quickly. All right, so I wanted to start by talking a little bit about these central measures of the storm, in particular storm tracks data. Tropical cyclones, we have to remember, are weather systems that are organized. As a result, they often are going to be tracked as a system. So a lot of times we think about temperature or something like that, and we think about having these different locations that get measured. That happens to some degree for tropical cyclones as well, but a lot of times we think about them, we globally as scientists, as a whole system. So here's an example of Hurricane Florence, and you can see this is a satellite image taken of it. These are beautiful images to see the storms like this. And you can see just by looking at it that it is a very, like it's a thing. You know, you can kind of separate it from other systems or weather patterns that are around, and it clearly has a structure to it as a single storm. As a result, one way that scientists often will track that whole system of a tropical cyclone is to take central measures of it. And those include measures like the location of the center of the storm, and then also its intensity at the highest point throughout the storm. And that point's typically near the center. So if we go back and look at Hurricane Florence, we're looking at this whole immense system that's very, very large, but a lot of times the primary measures that we talk about as we're tracking, as we're forecasting, and then later as we talk about it historically, a lot of times you'll hear a focus on where the eye was, just this one part at a specific point in time, and then what the most intense winds were, which is often going to be somewhere just outside of that eye, on right-hand side if you're on the northern hemisphere. Some of these central measurements that you see a lot and that you see so often when you talk with your friends who aren't scientists about this, they've probably heard at least of this part, are scales like the Saffir-Simpson Hurricane Wind Scale. And these talk about the storm, again, as a whole. They put them into categories, and these are linked to the damage, and they're linked to the intensity of the winds. But it's important to remember that, again, they are just a measure that's central and storm-wide, rather than being something that captures the full spatial pattern of each specific storm. As we track a storm, a lot of times we will gather these central measurements at regular times, and these are known as the synoptic times. So they're taken at midnight, 6, 12, and 1800, which would be 6 p.m., with coordinated universal time. And for many of these tracks will cover several days, in some case a week or more. These storm track data are widely available, and they go back many, many years, so you can get a lot of historical information from them. When you want to work with them, often you will be able to get almost real-time versions of these storm track data for a storm that's in progress. However, that tends to be a preliminary version, and then at the end of the season, a lot of times meteorologists will get together and do what's called a best tracks version. And I have never sat in on this, but my vision of it is that there are a bunch of really smart meteorologists and atmospheric scientists who pull together all of the data that's involved in each specific storm, and they go back and they look at the preliminary track. And at that point, they might change things like the location of the storm at specific points, and also the intensity based on better information and better data that they might have been able to pull together between the time that the storm was being forecast and the time they update these best tracks. So a lot of times, if we are working within a specific tropical cyclone basin, we might use the best tracks that are from the Weather Service that did that. However, there are also ones that are available internationally through an effort that's called the International Best Track Archive for Climate Stewardship. The acronym for that, I pronounce it as IB tracks. I'm not sure if that's right or not, but I guess I will spread that to all of you. So if it's not the right way to say it, it'll at least be how health people say it. So to talk about IB tracks, we need to step back and talk for just a second about tropical cyclone basins. So storms can happen around the world, but they don't happen everywhere in the world. They tend to happen in pretty specific areas. For example, a lot of the ones that affect the eastern coast of the US, probably all of the ones that do, are generated in the North Atlantic Basin, and there the storms are called hurricanes. As we go in other areas, like the Northwest Pacific Basin, they might be called typhoons. In the North Indian basin. They're called cyclones and so on. Now, traditionally and historically, what happened was that different weather services were responsible or became responsible for tracking these different basins, which is wonderful. It is spreading out the work across a lot of different places, a lot of different countries. However, it creates some limitations when you want to do large-scale studies that are using multiple basins. These different weather services will sometimes measure things in a different way, or they might use slightly different scales, things that are alternatives, for example, to the Saffir-Simpson scale. As a result of that, you end up having a hard time comparing things. One of the things, for example, that is very subtle but that can be different is the averaging period when calculating wind speeds. If you talk with the meteorologists, they can talk in great depth about the differences that might make in the winds that you put in your measure. But at the end of the day, it means that the measures for some basins, if you take the data from the weather service that was in charge of that, might be all offset a bit from another one because they were doing these different averaging periods. Fortunately, this issue is addressed by IB tracks. This brings together global tropical cyclone storm track data, and then it does a lot of the work to standardize across those differences from the fact that it's being tracked by these different weather services around the world. And it gives wonderful data sets that you can use in a comparable way as you work on storms that are in different basins. So my recommendation, if you are studying storms in a single basin, for example, if you are studying the impacts along the eastern coast of the United States, it should be fine to use the specific tracking data from the Weather Service in charge of that. And in fact, as we go through and look at examples, we'll be using data from the U.S. National Hurricane Center, which is the agency in charge of tracking storms in the North Atlantic Basin. However, if you're looking at multiple basins, if you're doing a study that's moving into a global scale or using multiple countries that are situated in these different basins, or even are in a country that might be affected by storms in different basins, it's probably best to start using the IB tracks data. If you do that, it is a wonderful data set, but there are a lot of subtle details to it. So I strongly recommend that you read through all of the documentation that it has available, including its README documentation, any white papers, things like that. There's also an excellent paper. It's from about 15 years ago now, but still really, really interesting to read. And it goes into the motivation and even some of the history of tracking tropical cyclones and why there is the need for this IB tracks and how it is managing that kind of standardization. So as I mentioned, in the US, the best tracks data are available through the National Hurricane Center. And my group put together a couple of packages called Hurricane Exposure Data and Hurricane Exposure that make those accessible in R and provide some functions that make it a little bit easier to work with them when you're doing epidemiology studies. We'll start by talking right now about how you can pull information about these central storm tracks from them, but where they really start to shine is the information that they have from wind field modeling, which we'll move into talk to next. If you are doing something that is outside of just the US, because that is only covering the US, there are other R packages available that can help you access the IB tracks data. There are also efforts underway, including one led by Robbie Parks, to take some of these wind field models and create more global exposure assessment for tropical cyclones. So I'm going to briefly talk about the setup. Again, I'm not going to take a lot of time on this, and I'm not going to kind of like wait. I don't expect you to be coding as you do this. This is more to allow you the chance to take a few notes if you want to, so you can come back and try this on your own after the workshop. So if you do want to try this, it does run through R, and so you'll need to have R, and I highly recommend also having RStudio, which is an integrated development environment that just makes it nicer to use R. The data package is not shared in the normal way through the CRAN archive. Instead, it was a really large data set. So I worked with somebody named Dirk Edelbutel, who had created a way to share large databases, large data packages through something called DRAT. So if you ever want to know the details of that, we wrote a whole paper about how this works. But also, mostly what you need to know for right now is that you're going to need to install the package in a slightly different way than you normally would for another R package. So it's going to be installed from our personal repo, which is up on my GitHub, which is under GE Anders. And so what you'll need to do is install the package drat, which you do install the normal way, then call library drat, and then you can run these lines of code, and that should bring in the hurricane exposure data. This R package has only the data, and then we also created one called hurricane exposure that interfaces with that and provides some of the functionality. That you can get from GitHub, and you can install it using DevTools, and then library DevTools and install _GitHub. Now, the main example package that I have up is only covering storms up to 2018, but if you are really ambitious and want to dig around, you will find that there's a development version of the hurricane exposure data where we have some more current storms as well, which you are, of course, welcome to play around with, and hopefully we will move that into being the primary one fairly soon. All right, so I can give just a few examples of how you can map some of those storm tracks and pull information from them through this package. So once you have installed the packages, you'll need to load them, which you do in the normal way. And I also typically will use the tidyverse package for working with the data. There's a function called map tracks where you can put in the identifier for the storm, which we do as the storm name, a hyphen, and then the year of the storm, because storms, you can have the same storm name over multiple years until that name is retired. So this is an example of plotting the best tracks for Hurricane Sandy. You can do this with multiple storms if you want to get an idea of the exposure over a longer period. And then you can also work directly with the data set. You can use data HurTracks to pull in the tracking data itself, and then you can work with it as if it were any other data set. You can see some of the information that are included are the storm ID, the date of that particular tracking point, and then you've got information about the latitude, longitude, and the wind. There will be multiple lines for each storm. Here I've randomly sampled just 3 points from the whole data set, but for example, Dolly would have multiple lines where it has the date, and then this best tracks information of latitude, longitude, and storm-wide wind throughout the whole tracking period. Again, you can work directly with this data set, which means you can do everything you want to do in R. So for example, one thing R is very good at is doing regular expressions. My name starts with B. It has always been my dream that someday a hurricane will be Hurricane Brooke. I could look and see if that's the case by using regular expressions with a filter to look for all of the storms that start with the letter B and then pull some information about them. Spoiler alert, there has not been one yet, but maybe in the future. By having this data in R, I think one of the big advantages is you can leverage all of R's other useful packages. And that's not just for these central storm tracks data, but also for the other stuff we're going to look at in terms of the wind fields and other hazards later. So some of the ones that I strongly suggest if you are using R for your own work are the SF package for mapping and working with geospatial data, the tidyverse for exploring and plotting data, which I think is widely used and widely taught now, and within that, most specifically the LubriDate, which is helpful for working with dates and times, because one of the things that becomes tricky in taking weather-related data and merging it up with health data is often the weather data is in UTC or some other centralized time zone, whereas often the health data is linked through to a local time zone. All right, so now that we've talked some about those central measures that I think many people, not just epidemiologists, not just people in weather, I think many people are very familiar with those things like Category 5 as a very strong storm. But I want to talk about for epidemiology how sometimes those aren't the best ways for us to measure exposure, directly at least, and instead it's very helpful to think about local ways to measure some of the hazards. So the tracking data, again, can give you these central measures of the storm, but that doesn't always give you what you want for an epidemiological study. For example, if you think about a location that is off the track of a storm, but close enough it might be affected, you could have two storms that were at the same location that had the same central intensity, but one of them could be very compact and small and not spread out very far, and another could be very large and sprawling. And as a result, for these locations that are not on the central track, for the smaller storm, that location might not be affected at all, whereas for the larger one, it might have a big impact. This highlights a really important point. A lot of the people who might be affected by a storm don't live right on the storm's tracks. And the central measure of the storm really isn't helping to capture the exposure in a way that is anything other than kind of like back of the envelope for people that aren't living along the storm's tracks. So it often can be not the best way to be able to capture exposure when you have a population you're looking at that weren't all right at the spot of landfall or all right along the track of the storm. What we can start looking at there instead is the wind field of a storm. And I apologize, this is a little bit grainy, but I feel like it was a good illustration of this idea of a wind field. This is for Hurricane Matthew. I believe it's taken based on observations rather than a model. And what happens with a wind field is because these are so well structured, you of course can see the system itself, you can see its center, but you can also see the intensity of the wind, which is shown by color, at points moving away from the center. So it's giving a fuller idea of the spatial hazards related to that storm. You can also get information from that about the direction of the winds, and these little flags are all related to the direction that the wind is blowing. So this is the wind field itself, which you can get and develop based on observations. But there are also models called wind field models, and these are parametric and were built to estimate these wind fields. There are a few that you might have heard of. The one that we'll be talking about with the examples today is called the Willoughby model, based off a scientist named Willoughby who developed it. But another one that's very popular you might have heard of is called the Holland model. At the heart, each of these are giving a kind of smooth modeled way to get storm intensity in terms of the wind hazard as a function of the distance from the center of the storm. But it's not quite that simple because these storms aren't symmetrical. So tropical cyclones are rotational systems. And a lot of the real intensity of the wind is in the rotation, but you're getting some of it from the fact that the storm is moving along in a forward direction. So we call that forward movement of the storm the translational movement, and then we call this other the rotational. But because you have these two components going together, the wind speeds won't be the same everywhere in the storm. You will have higher wind speeds if you're in the northern hemisphere on the right side of the eye in the direction that the storm's moving. And you'll have lower on the left, and that's because of how the movement of the storm is either adding to the rotational speed or taking away from it. If we look at a profile of a storm, this is saying what the wind speed, which atmospheric scientists will often talk about as Vmax, is in relation to the distance from the eye of the storm. So you can see that on the right-hand side, as the storm's moving forward, that this gets higher, and then on the left-hand side, it stays a little lower. And then outside of that asymmetry, you have this pattern that right near the eye, there's very low wind, and then it goes way up, and then you have a more gradual decrease in the wind as you get further away. When you do these parametric wind field models, what they're taking are our old friends, those storm track measures. So it's using information about the location of the storm over time, because that's something that it can use to calculate the translational direction of the storm, and then also the translational speed of the storm, how quickly it's moving forward. Those are important components to bring in to calculate or estimate these winds. It also will include, as its input, some measure of that central storm intensity. For some models, that will be the maximum sustained winds in the storm, and some models will actually base it on the minimum pressure in the storm. Those two factors are very strongly associated with each other. So when these wind field models are developed, of course, they start from data somewhere, and then those parameters get tuned based on real observational data. And so I want to make sure we remember where some of that's coming from, because I think that's really important in thinking through where there might be some limitations to this. So a lot of this data, and also the original optimization of these models, some of the original intent of them, was to get a really good estimate of what the wind speeds and the intensity of the storm might be right before it makes landfall and right when it makes landfall. One of the ways that they do that is through what's called flying the storm. They take airplanes and they fly them into the hurricane, and they drop out what are called dropsons. This picture is an example of one. This is actually not the plane that would go into a hurricane, because this is a NASA plane and it's National Hurricane Center that flies there. They're called hurricane hunters that they fly into the storm. But this was the best picture I had of this. So once they're up, they'll drop them out, and as that thing comes down, it's collecting data along the way that goes in to inform the models. There will also be some field campaigns where people might take a lot of weather monitors that are very sturdy and hardy and locate them near the coast where they anticipate the landfall. Now, for these dropsons, you can't collect them over land because you don't want those to hit a person or hit a house or anything like that. So all of that data is over the water. And similarly for things that are taken right near the coast, they're often not representative of what conditions and what the wind relationship might look like as the storm moves further inland. Another thing to note about these wind field models is that you can use them not just to get the storm track and what was happening along that, but any location the storm might affect. Now, in some of the data we'll look at in a minute, we will look at how we can use those with data that's already kind of been pre-processed to look at county level or zip code level, where the wind model's been run out to the centroid of each county or the centroid of each zip code. Those are really helpful if you have health data that is already aggregated to that level. I want you to keep in mind too, though, that the storm wind model itself can be used and run to any grid point locations you want. So if you had a study where you had the residential location of each study subject, there's nothing that would stop you from running wind field models out to each of those residential locations. It would take more computer time, but there's no practical reason outside of that you could not do that. Another thing to keep in mind is that a wind field is representing a single point in time during the storm. So this is an example again from Matthew that we saw before, and you can see this is just what the winds look like right before the storm made landfall. If you want to look at different locations, you might want to see what the winds looked like throughout the whole period that the storm was coming through. You can use wind field models to do that, and the way to do it is to repeat the wind field modeling at lots of different time points throughout the storm. Often we'll do it not just at those synoptic times every 6 hours, but we will interpolate the storm track between those to every 15 minutes or so and run the wind field model every 15 minutes. And then at every grid point location, we can get this kind of profile of how it changed over time. This is an example for Hurricane Floyd in Dare County, and you can see as the storm was far away, there was no wind from it, but then as it got closer, it increased and there was a sharp spike when it was very close, and then it came back down. With this kind of profile, you can get some different pieces of information. One is what the peak local wind speed was throughout the storm, which you might use as a measure of intensity. Another that could be interesting is how long the winds were above a certain level. For example, from this, you could pull how long wind was modeled to be above 20 meters per second in that location. There's some thoughts in terms of engineering that the longer you have wind speeds above a certain level, the more property damage you might have, because you've got a repeated kind of like pressure on the infrastructure as you continue to have that wind. So those are all things that can be pulled from a wind field model. In the example data sets, the main ones I'm talking to you about, we have the results from running these wind field models for historical data. As I mentioned, it's up to 2018 in the data set that we have as the main one, but we also have a development one that goes longer than that. As a result, you can do things like select a storm and then map the counties and get wind speeds that were modeled in terms of the peak wind speed that was ever achieved during that storm at that location. You can also pull the data to use directly and to integrate with health data. So this is an example of pulling some from Hurricane Ike, and you can see that you're getting this FIPS code, which is for the county and can be used to integrate with other data. Another piece that's useful for that is you can get the closest date. So this is the date that that storm was closest to that location. And because these storms are large and take a while to go across the country, that date can be different for different locations in your study. These have been converted in this data set to be in the local time of a specific location. So you can get it in the UTC if you want, but you can also get a version of that that should be aligned with health data that is collected based on local time. A growing number of studies have used these wind field models to assess exposure to tropical cyclone-associated winds. And I'm really excited about this because I feel like about 10 years ago, it was really hard to find any epidemiological research that was using this kind of approach. And I think it's a very strong one for capturing the local exposures. We saw some of them in the earlier talks today, but I've also put in some references for different ones, including studies of mortality, hospitalizations, infectious waterborne disease, and then also school outcomes, so things that are going beyond epidemiology to some other health impacts. All right, the next thing to keep in mind and think about is when you use these kinds of models, you will get a continuous measure of wind, but you will have a choice of whether to keep that as a continuous measure or to convert it into a binary metric where you're classifying as either exposed to the storm or not exposed to the storm. To date, most studies have looked at an exposure as a binary variable. One exception is a study by our very own Dr. Nethery, and I'll show an example of that in a minute. And in this study, we're both involved in it, we found there's evidence of an exposure-response relationship that is pretty nonlinear. So I think that's really interesting and exciting research. But I do have to say that this is important to estimate these kinds of exposure responses, but it's not very straightforward. It's often methodologically difficult, both because we have nonlinearity in that, but then also the data is pretty sparse. There aren't all that many exposures, certainly compared to something like temperature. And then the really extreme exposures are even sparser. So we can look, this was a study based on the Medicare population, and it's looking at some different outcomes, including mortality, respiratory outcomes, COPD, and CVD. And you can see at the bottom that we have this as a function of the maximum sustained wind speed. For many of these, you'll see it looks like there's evidence of a kind of threshold effect where it might be linear above a certain level, but it is certainly not up to that level. The bottoms of these also show a log plot where each tick is showing a specific exposure. And you can see that as we get out to many of these higher values, they just become very, very, very sparse. So I think because of some of those challenges, hopefully we will continue to work on those and continue to do more work in getting exposure response functions based on the wind speeds themselves. But a lot of times we do see studies that are using binary exposure, and those certainly still give really important information and insight. If you do that, you need to pick a threshold to define the exposure. One common practice in many studies to date has been to pick a threshold for the main analysis, but also explore some other selections of threshold for exposure to start to get at that question of potential for exposure response. For example, a study might conduct a main analysis using gale force wind speeds, which would be 34 knots, as a primary study, but then also consider what results look like when they use hurricane force wind speeds. As a note, the names that we're using here, things like gale force, come from something called the Beaufort scale, which if you are using wind field models and using thresholds, I strongly encourage you to take a look at that and become familiar with it. It's a scale that takes different wind speeds and it puts on them a description of what's actually happening on the ground. And these, of course, aren't perfect, but it gives you some idea of what a local wind speed translates in terms of the potential for damage and the potential for effects. So you can see they have very evocative descriptions of it, where the strongest is the hurricane force, where you're going to have really extreme damage to buildings. But you also have things like gale, where you are starting to have damage to trees. Having these descriptions makes it really useful as you are thinking through what threshold might be appropriate. So for example, if you hypothesize that power outages might be a key player, for example, maybe you are looking at the compound effects of heat and you think they're going to be particularly bad if the storm causes power outages and increases the exposure to outdoor heat for people who normally have air conditioning. At that sense, something like the gale force might make a lot of sense as the threshold, because as you're getting to that level, you're starting to see power outages, damage to trees, and the result that that damage to trees can have in terms of knocking out power. If you're studying something else that relates to major damage to personal property, to buildings, to infrastructure, then you might want to look at a higher threshold. So all of those are things that I think are important to think about as you select that threshold. Regardless of which one you pick, do keep in mind that most of your storms, whatever you pick, most of the storm exposures are going to actually be right above the threshold that you picked. And the reason for that is that these exposures are very strongly right skewed. We saw some of that in the plot from Rachel's paper earlier, but this is another example from a paper led by Mei-Lin Yan. This was looking over many years at exposures in the United States. And you can see this histogram is showing the number of exposures at different levels of the wind intensity. And they're left skewed if you do a strong gale as your threshold. If you move up and you do a hurricane as your threshold, it's still going to be right skewed where most of your exposures are closer to the threshold and just a few are far from it. Studies that have considered multiple thresholds often find some evidence that there's an exposure-response relationship in terms of finding that the estimated risk is higher when you use a higher threshold. But because these are so skewed to only having a few at the really high exposure levels, it means that often if you pick a higher threshold, you're going to be estimating with a lot higher variability. This is an example again from the Yan paper, and I won't go through all of it, but I just want to focus on these winds. The circles here are for cardiovascular effects on hospitalization and the triangles for respiratory, and this is in the Medicare population. Here, different thresholds were selected, and you can see, especially for respiratory, as we do a higher and higher threshold, you are getting a higher and higher relative risk, but you're also getting those confidence intervals moving wider and wider and wider. And this is a pattern that if you start looking for it, you'll see over and over again as people do these studies that investigate a lower threshold and then investigate a higher threshold. So the package has functions for working with this as well. The map wind exposure will let you put in what your threshold is. This is in meters per second. And then it will map which counties were above that threshold and so exposed. You can also do that to go through and get the exposures, for example, for every county in a particular state. So to do that, you can create a subset with the FIPS codes for that state. And then you can run it through and specify those counties and your limit, and you can get out data sets that will give every county that was ever exposed under that limit, what storm it was exposed to, and the continuous measures and dates that it was exposed. So as a note, and I mentioned this briefly earlier, the hurricane exposure data package provides historical data where the wind field modeling's already been processed. You don't have to do it yourself, and it's modeled to the population weighted county centers. That's really convenient if you have county level data for the same years that are covered by that. But if you don't, or if you want to model the residences or something like that, we also have a wind field model, and I won't get into it here, but I will give the name. It's available through GitHub, and it's called Storm Wind Model. That will let you run the model yourself. So you could generate any of this yourself, and the only downside to it is it's a little bit more complex to run the code, and then it takes more computational power to do it versus the ones that have already been processed. So there are both advantages and disadvantages to using wind field models for exposure assessment in epidemiological studies. Some of the advantages are that it estimates local, where the people are, rather than storm-wide or centralized estimates of exposure. It does provide a consistent method to estimate that over a study period, which if you're doing storms over many, many years, is a really big advantage and really important. And to some degree, it also is consistent across the study area. However, that's where we get a little bit into the disadvantages. So it is based at heart on a wind field model, and no model, of course, is perfect. These models were optimized by using data that was taken over water or right at the coast, and that's not where most people live. So unfortunately, these models perform pretty well for landfall, pretty well for storms that are really well organized, but there's some cases where they start to perform more poorly. That includes when they're traveling over land, or if you have a storm that's undergoing something called extratropical transition, which is more likely as it gets more northern or deep in the south if you're looking in the southern hemisphere. Also, there are just some tropical cyclones that have very unusual wind patterns, and it's going to smooth over those as any model will smooth over things that just are a little wacky compared to the normal. I can see I have a few more slides talking about some alternative methods of exposure assessment, but I do see where we started late that we are right at 1 now. Rachel, would you like me to continue? It's probably another 5 to 10 minutes, or would you like to stop here and do questions?
I believe Rachel had to step out for a call at 1, but you are more than welcome to keep going. We are recording this, so even if people have to step out for their schedule, the video of it will be available on our YouTube, so people can follow up with it at another point. So I think that we can definitely keep going.
All right, so I will get through this quickly and then we'll do our questions, but I think it is very helpful. So the last little piece I wanted to talk about are 2 alternative ways that you can do exposure assessment. Broadly, we'll talk about it. The first is other ways to measure winds, and then the second is looking at other storm hazards. So for the wind exposure, especially for the North Atlantic, so for the United States, for Mexico, for Canada, one thing that's available that can be really interesting to look at are called the wind radii. So these are ones, you can see each of these is kind of looking at a time stop as I believe Hurricane Katrina made landfall. And at each point, the wind radii will say in each of the 4 directions of the storm, how far a wind of a certain intensity reached from the center of the storm. These are not done based on a model. These are done based on experts going back and looking at the data of the storm and generating these based on the best data for that specific storm at that specific time point. So it captures these winds regardless of if it was undergoing extratropical transition, regardless of if there was something unusual about that particular storm. So it's really helpful in getting past some of the barriers you might have with a model-based approach. You can use these then to go through and take all of the counties within a certain degree of that radius and mark them as exposed. And we talk in our vignette for the hurricane exposure data about how we did that in the selections we made. So as I mentioned, these are through data integration and expert assessment. They're not based on models, and so they are not prone to some of the same limitations as the models. However, there are some disadvantages. One is that they may not be available for every storm or in every basin. So they might not be something you can use for global worldwide studies. They're also not available immediately because they have that expert assessment. There is a certain time lag before they become available. The amount of data that they're based on might vary by storm, and I don't think they're available for storms before 2004. And finally, they don't give you the exact value of the wind speed, they only give you categories. And it's not a binary category, it's more levels than that, but there still is a lack of granularity. So one thing that we did is we looked at some historical storms and compared the modeled storm winds to these wind radii and looked to see what % of the counties exposed fell into the same exposure category for both. For many of the storms, especially the ones that were smaller, exposed smaller numbers of counties, the agreement was really quite good. But there are a few where it was pretty far off, and some of them are these kinds of storms that make big impacts as you get further north in the United States, including Hurricane Ike in 2008 and Hurricane Sandy in 2012. We can look at those more closely. You can see modeled here, you can see extended best tracks to the right based on this wind radii, and then each storm is shown here. And you can see that the model tends to expect it to behave a little bit more symmetrically, a little bit nicer, and it might be similar for landfall along the coast or not very too much, but especially as we get further north, we're seeing a lot more asymmetry in the actual storm exposure. And in the case of something like Sandy that had really undergone a lot of transitions and was kind of messy by the time it made landfall rather than this well-organized storm, you can see that the actual wind radii are very, very different from the picture that you might get in terms of a more well-organized storm based on what you see from doing a wind field model that's parametric. So you can get these in the hurricane exposure data sets. And the way you do it when you do map counties is you can choose the wind source to be extended tracks, because the data set that those come from for the North Atlantic Basin are the extended best tracks data set. That will then categorize each of your counties based on where they fall in those different categories of the wind radii. Finally, of course, damaging winds are not the only hazard. This is for Hurricane Florence. It's outlining some of the different hazards. You have storm surge near the coast. You have flooding inland. You can have tornadoes. Here I've chosen to focus only on the winds just in the interest of time and to be able to dive more deeply in that. We see for some storms in particular, though, that these patterns can be really different depending on the hazard you do. This is, I believe, for Hurricane Ike, and you can see with the wind-based metric that things are really located close to the landfall. But if you look at rain-based metrics, flood-based metrics, you see that things extend way inland, and a lot of them are to the left of the track, and a lot of them are getting fairly north. Then if you look at the tornado-based metric, a lot of the tornadoes are happening on the right edge of the storm, which is actually a pretty common phenomenon. So you could end up with very different pictures of which counties are exposed based on which metric you do. Some of this is available in the hurricane exposure data set for you to play with, for you to explore, but also I want to make a note that you might find interesting information in other data sets about these hazards, flooding hazards, things like that. And what happens is a lot of times what you need to join that with the hurricane track itself is you need information for each of your study counties about when the storm was closest to that county. So one of the things you can do with the data set, if you want to interact with other data sets you find, is you can get information about what date the storm was closest to each separate county you might explore. And again, because these storms are so large and cover such a large area, it can take several days for the storm to pass. So there's not a single date for a storm that affects the United States. Instead, it really depends on what part of the United States you're looking at. And you can pull that information to use to merge in other data sets using the package. Here's an example there. For that, you would use the county distance function, and that allows you to set specific limits for how close something needs to be before you include it in the data set. So I will end with that. I will stop sharing the screen so I can look at all of you again, and we'll see if there are any questions.
Thank you for that. That was incredibly insightful and very easy to follow. I really appreciate you providing us with this
Into the TikTok, right? Yeah.
And the slides, even beyond the people who are able to join us here, I think that's going to be a really, really helpful resource as people come back to this video and the materials that you provided. Yeah, if anybody has any questions, you're able to raise your hand or unmute yourself. If you don't feel comfortable with that, you can put a question in the chat and we'll go through it, but I'll give a little bit of space to see if anybody has any questions. We have a couple people who are off mute, so I don't know if they're prepping questions or.
Oh, I see one as well in the chat. So the question is about Hurricane Maria. Yes, the data that we have in the hurricane exposure data is the continental U.S. only. So I think it also does not include Hawaii, which is actually in a different basin, and it does not include storms in Puerto Rico for the version that we have. When we were first developing it, the wind field model was specific to that area because one of the components it includes is a land water map, because you have differences in how things get calculated when the storm's over land versus over water. In the more recent version that we've done of the storm wind model, the development version of that, we include a map that's global for that kind of land mass part of it. So it's certainly, the storm wind model could be run directly for Puerto Rico. It's not included in that pre-processed data, but for Hurricane Maria or for any other storms that you wanted to do anywhere that you have the tracking data for, that kind of like best tracks or IB track style data, you could input and you could generate them yourself. And that's in the package called Storm Wind Model, which has a vignette with a lot of details for how to go through and do that. But thanks for that question.
Any other questions from those who are here? If not, I'm sure that you'd be more than welcome to follow up with a question. Oh, I did see somebody come off mute. Hang on, I think there is a question.
Hi, Dr. Anderson.
Hi.
Thank you for your talks, and I use your data for my analysis. It's been really helpful. And I was just curious about the data set in general, like were there any other like metrics you considered but didn't include in another, like your data set? Were there any other options you considered?
Well, we thought about a whole lot of stuff when we were doing it, just trying to figure out the best way to do everything. I think we have captured, well, one thing we thought about using but ultimately didn't include, some people will use FEMA disaster reports, which can be helpful in characterizing the actual impacts of the storm, and the data are available. Some of the downsides are that studies have found that sometimes what gets classified in that can have a political component to it too, in the sense that you might have like kind of stark boundaries right at a state line where one governor was able to advocate for help from FEMA and the other one couldn't quite do it, or things like that. So there's some, you know, it's getting a little bit further and further away from the forces themselves and getting more into the response of it. So that's one that we considered. And then one that I think we've used to explore stuff, but I think is more limited and would love to have better sources, and I think better sources are becoming available, is for the flooding. Flooding is clearly very, very important. And what we have in that is based on the NOAA Storm Events database, which is helpful, but it's a database based on reporting. And if you look through that historically, if you look through it spatially, I think there are some biases in that. So I think there have been movements, and maybe somebody else can comment some on this, but I think there have been some developments in things like flood databases that are based more on remote sensing and might be a little less prone to reporting bias types of stuff. So that's one where it's in there, but when we were writing up the paper about it and writing up the documentation, we do include those caveats that it's probably better than nothing, but has more limitations, I think, than like the rainfall or the wind field modeling that's included.
Yeah, thank you so much.
Mm-hmm.
Okay, I think we'll go ahead and wrap it up there. Thank you again so much. This was so informative and very, very helpful. And thank you to everyone who spent some time with us today, whether just in this session or throughout the day, talking about the intersection of hurricanes and health. A lot of these materials will be available on our website in the coming days. And thank you, Dr. Anderson, for also sharing the materials from this one. And we look forward to seeing you all in future cafe events. But thank you so much for your time and your attention.